I've come to a handful of meetings like this and just given a quick overview of how these lithium-ion batteries work, and I can also talk about supercapacitors at the same time because they're actually pretty similar. And then we can basically open it up to some specific questions you guys have in the context of the testing and the implementation that you're doing. Does that sound reasonable?
Sure.
Okay, great. So let me know when I can start, and I will.
Start when?
I would have worn a tux or something today if I had known that I was going to be... So there's a couple of... So lithium-ion batteries are very simple, all right? And as the name implies, we use lithium ions as the main charge carrier within the construct of the cell itself, okay? And we have... This is going to be my anode. And we have these, and this is a very common diagram that pops up whenever you do a web search on lithium-ion batteries and materials and function, okay? And I'm going to stick with the material system that you guys have in your batteries, your Thunder Sky batteries, which is at the anode, the cathode, it's LiFePO4, and at the anode, it's just graphite. Okay? Now, what makes these, why do we use these materials? What makes them special? And after decades of testing and use and optimization and so forth, the needs on the material are simple, but they also are very demanding. We need a material that can accept and reject a lithium ion relatively easily without a huge energy or voltage overpotential cost. But we need it to be able to do this thousands of times without changing the material so that it degrades or gets worse. Okay? That's what we need. We don't always get that, but that's what we'd like to have. Okay? Turns out that simple graphite, if you get the right kind, it's modified properly, has the right structure, can do that. And lithium iron phosphate also can do that. Okay? And when we make a lithium ion battery, the first thing we do is we put virgin graphite on a very thin foil on the anode side. It's never seen lithium before, and we take lithium iron phosphate powder or nano powder. It's spray deposited on a thin aluminum foil, so this is going to be aluminum, and our graphite powder is spray deposited or cast coated onto a copper foil, and they are the thickness of my material of my foils is probably under a mil, maybe 20, maybe 15 microns. And the thickness of my electrodes on any given side is somewhere between 40 and 100 microns. Typically in the 50 to 30 micron range is probably a typical thickness for the kind of high-rate batteries you guys are using. So these powders are coated on. All our lithium at the start lives in lithium iron phosphate. There's no lithium here, okay? And when the battery is fully discharged, all the lithium is back here on the cathode side, and a fully discharged battery has no lithium in principle on the anode side. Okay? So I'm going to right now put my lithium ions, and they're not really ions when they're inside the crystal structure, but I'm going to draw them as such just because we're talking about that. Now, these little things that I've drawn here, these represent crystal sites within the crystal lattice of lithium iron phosphate. It's kind of a complicated crystal structure, and I'm not going to talk about it because it doesn't really matter to you guys. What is important is that you recognize that this isn't a surface reaction. It's not a lead-acid battery. It's not a nickel metal hydride battery where you are sort of doing a phase change on the surface of a plating, or you're stripping a material onto a known electrode. You are instead having this relatively well-defined crystal structure with lithium that lives at these different very well-defined points. And what makes this material interesting, it's called an intercalation material, is that when you remove the lithium, it doesn't change its structure that much. It can take lithium in or give it out without altering very much. And graphite is the same. You put inside the basal planes. So graphite is a structure of these hexagonal carbon structures that are layered, and these layers are relatively weakly bound, right? And this is why we use graphite as a lubricant, right? Because you take advantage of the slip plane within the very easy slip plane in graphite. Turns out that because it's weakly bound, it also can open up or collapse a little bit, and it can handle lithium when you want to drive it into it. So this is our fully discharged battery. This is as we make it. So what I do now is that I charge it, okay? So I have different colors. Okay. Okay, I'll do red as charge. So, charge. I drive electrons this way, okay? And this is a constant current, right? I'm putting whatever, an amp through here, a milliamp, whatever, depending on the size of the system. And I'm driving this through, all right, coulombs of electrons. And when I do that, I put, before I talk about the charge, I missed one thing, and I apologize. We have to talk about the electrolyte. There's got to be some way for lithium to move from this side to this side. It's not going to jump through open space, obviously. So we have inside of here also some free lithium ions floating around. These come from our electrolyte. It is the same electrolyte for lithium-ion batteries as for supercapacitors, roughly. There are modest differences. What you have is a salt, LiFePO4, pretty commonly, dissolved in some kind of organic. So inorganic solvent. All right, and the organic solvent is ethylene carbonate, dimethyl carbonate, propylene carbonate, ... There's some mix of EC, DMC, DEC, diethyl carbonate. Don't worry about this. It's an organic solvent, all right? And it's sort of, it has the consistency maybe of gasoline or something like this. It is flammable, and this is where some of the problems safety-wise come with lithium-ion batteries. And but the good news is that this stuff has no water in it. It's not water sensitive. You cannot have water if you're going to have lithium floating around. It's a bad combination. Specifically if you're going to have any kind of lithium metal. But more importantly, when you drop in lithium hexafluorophosphate, LiFePO4, when you drop it in this organic solvent, it dissolves. And it dissolves into Li plus and PF6 minus. So you've got this Li plus is floating around and your PF6 minus is floating around. And so this Li plus that's on the electrolyte comes from dissolved lithium hexafluorophosphate in this organic solvent, okay? And this has been, again, fine-tuned over several decades now of lithium-ion battery development. And there's, multiple different ways of changing this solvent for low temperature, high temperature performance. You can change, there's other salts too, but I'm just going to use this one for now. It doesn't really matter for you guys. Again, very, very similar to what you'd find in a supercapacitor. And I'll jump to that in a minute, but I'm going to stick with this for now. Okay, so now I've got lithium stored here in my lithium iron phosphate. I've got no lithium in my anode, my graphite, and I've got some free lithium floating around in this organic solvent. And now I'm going to charge it, which means I'm going to force electrons down into my anode. When I do that, I build up local negative charge, right? And at the same time, I am stripping electrons from my lithium iron phosphate. So what I'm going to actually do, the lithiums actually are not ions, as I said, inside my lithium iron phosphate. But when I pull a current from it, I am pulling electrons out of this material. And it turns out that the person with the short stick is a lithium. And it ends up becoming ionized. So these electrons, as I charge, are actually ultimately coming from where the lithium is in the system. So when doing that, I free up the lithium, and lo and behold, I also have now a negative charge building up on this side. Opposites attract. This lithium is drawn into this graphite structure, okay? So as I charge the battery, I move lithium. The net result is all this lithium is moved from the cathode to the anode, okay? So what's this look like? This is the bread and butter of battery research, is the voltage profile plot, right? So it's voltage versus capacity in amp hours, which equals coulombs, right? Okay. Question?
Sort of equals coulombs. Amp seconds.
Amp seconds, yeah. Well, amp hours, yeah. Equals some constant times coulombs. Agreed. Fine. Yeah. Is equivalent to, nominally. All right, fine. And we start at our open circuit fully discharged state, which is something like 1 volt. And that's just the natural equilibrium surface potential of our lithium iron phosphate versus our graphite without anything. And it quickly does this. It jumps up and gives us a plateau, and then goes up like this, okay? So and this is a sort of idealized lithium iron phosphate charge curve, but you've seen data similar to this both from the manufacturer specs and also from probably your own testing. And this is about 3.4, 3.5 volts, okay? So there's this plateau. And what's happening is as I'm going up, I extract this lithium out, and I reach this place where I have there's a phase change that occurs between lithium, iron phosphate, and just like when you boil water and you go to change the phase between liquid water and gas water, you have a constant temperature which just occurs. We're doing a phase change here. We're going from lithium iron phosphate to iron phosphate. By doing that, by virtue of thermodynamics and the Gibbs phase rule, we lock in the voltage at which it occurs. Okay? So in this range, we have a coexistence of lithium, iron phosphate, and iron phosphate. And up here, when it starts to curve up again, you've exhausted all the lithium out of the system, and you are left just with FePO4. Okay? And so that's sort of what's happening. And within this voltage range, you are enacting a phase change between lithium iron phosphate and iron phosphate, and you're doing it by removing the lithium from the lithium iron phosphate crystalline material and extracting it into the electrolyte and driving it into the graphite that's over here on the anode side. Okay.
Is this curve characteristic of all batteries?
This curve is characteristic for only lithium iron phosphate. Lithium cobalt oxide, which is what we have in our cell phones and so forth, is more slopey, and it has a different kind of phase transition representation. And it's also has a plateau, if you want to call it that. It's more slopey in general, but it's more like 3.7, 3.8 volts, right? Which is good for energy, because of course energy is integrated power over time, and power is current times voltage. But it's not necessarily as good for safety. And this is one of the reasons why people are looking to lithium iron phosphate for automotive applications, is because by virtue of having this lower potential, the electrolyte is more stable, and there's much less chance of evolving gases that could lead to venting and combustion, right? So there's this trade-off that occurs. Plus, lithium iron phosphate is relatively inexpensive compared to lithium cobalt oxide. Cobalt is not so cheap, although there's many costs associated with fabricating nanostructured material that is still can drive the cost up of any of these things very easily. So this is what's happening, right, on the charge. And when we're up here, all the lithium, in principle, is gone from our lithium iron phosphate, and it's all over here. So we've got iron phosphate, and then we've got LiC6. So for every 6 carbon atoms that we have in our graphite, there's 1 lithium sort of stuck inside. So we go now from, and this is why it's called a lithium-ion battery. In fact, the only lithium that exists in this system free are the ions that are in between. At the cathode and the anode, we are actually intercalating. The word is intercalation. We're intercalating lithium into the graphite during charge, and we're deintercalating it from the graphite and reintercalating it into the cathode during discharge. Okay? And this potential, why is it 3.4 volts? It's a natural bit of thermodynamics that this transition between this and this, LiFePO4 and FePO4, occurs at 3.4 volts. It's the redox couple reaction. It's a lookup table kind of thing, just like any lead acid redox couple or nickel metal hydride redox couple. The redox couple for this and this electrolyte against this anode is 3.4 volts. That's just the way it is. Okay? So that's the raw sort of what's happening. And so how badly does this lithium want to go back into the lithium iron phosphate? It wants to go, its driving force is 3.4 electron volts, right? That's how badly it wants to go. And 3.4 volts is quite a bit. It really does want to go back. So if we then provide if we stop charging it, if we take our power supply off and we leave it open circuit, right? If it's open, we have an open circuit voltage of something like 3.5 volts if we're fully charged, right? And no current can flow. And because no current can flow, even though for 3.4 volts worth of energy, these lithiums want to go back here, they can't, okay? Now, if we then supply a load, we allow electrons to go this way, right? These electrons quickly, because they're accelerated through a potential of 3.4 volts, they zap up, they go through our load, they go back in here. When they do that, again, we're stripping an electron from the lithium that is reunited with the lithium during the charge, and it's ejected from the anode, and it goes through the electrolyte and reinserts itself into the cathode structure, and everyone's happy again. The lithium goes back to where it wants to go. The discharge looks like this. It has a very similar, although slightly lower voltage. I'm going to try to capture that. Okay? So this voltage is something like, I don't know, it depends on what and then now we're going to get to things you guys are really curious about, but I had to start with this. This is going to be something like, if you very slowly, it'll be something like, it depends a little bit on some of the specifics of the cell. Let's just say that it's 3.5 volts, okay? And this discharge is going to be something like 3.4 volts, okay? Maybe it's a little bit lower than this, but this is just an example, okay? Now, but it's a plateau, and these should look under very low rates. These should mirror each other pretty well. And the capacity we'd expect from lithium iron phosphate based system is something like 140 milliamp hours per gram of lithium iron phosphate. Okay, so if you ever wonder how much active material, how much lithium iron phosphate you actually have in your materials, you can say, well, I have this many amp hours. You can back calculate using roughly 140 milliamp hours per gram of specific energy, specific capacity, and you could figure out, well, I probably have that many grams, right? So basically, for every gram of lithium iron phosphate you put in the system, you can expect to get about 140 milliamp hours of charge capacity and discharge capacity. These should be very similar if you go at a low rate. And these voltages should be very close. There is a slight thermodynamic penalty to be paid, and that is manifested in the difference between charge and discharge voltage, right? There's a slight, this phase change between lithium iron phosphate and iron phosphate has a very small but very well-defined energy associated with it. And that energy is the difference between the charge and the discharge voltage. Okay, and that's going to happen no matter what, okay? So this is an idealized battery, and we have, like, let's say we have a single layer, an atomic layer of lithium iron phosphate here, and a very thin layer of graphite here, and we have no current losses, no potential losses. We have a superconducting system and a perfect resistor here, okay? Now, we all know this is not actually what happens in batteries. So what actually happens? First of all, I'm going to stop now. Does this make sense to you guys? Do you have any questions? What I'm trying to do is just quickly go through what's happening materials-wise, because it's actually really important to deconvolve the materials from how the battery is put together. And the parameters you guys are mostly curious about are more electrode and cell construction than battery construction. But you can't understand those until you have some sense of this.
So I have one question.
Please.
Maybe it's not content critical. I'm surprised you didn't draw the green curve under the red curve like you would in a transformer.
Oh, you mean just like down here?
Yeah. Is this leading up to something?
Well, not really, but when I do my testing, I always do a plot of voltage versus time.
Over time. Okay.
And because I do a charge and I do a discharge, right? And my current goes like this, and then it goes like this.
Yeah.
Right, so this is how I look at it usually. For me, it's easier to piece together, but indeed, other folks do, in fact, do this, and it looks like this, right?
Yep, and then you talk about the energy loss.
And that's right here. Right, you can actually integrate this envelope, and it tells you where, and that is the thermodynamic at infinitely slow rates. That's the thermodynamic penalty, right? That's the loss of Gibbs free energy that you have associated with this phase change that you do right here. Okay, good. So that is the ideal battery, right? So we're going to draw a line here because now I'm going to map over to what we have in our cells what we do. Okay, and I'm going to motivate this, I think, with an equivalent circuit diagram first. So. That's a perfect battery, okay? This is what we might draw as we draw batteries and circuit diagrams, right? But in reality, a battery is, at minimum, this. And in fact, it usually has what we call a Warburg constant here as well. Okay, this is actually a battery. Okay, this is a series, and there might be another resistor out here too. It depends on how you bookkeep things, and there's a variety of equivalent circuit models that we might want to carry. And has a small capacitance associated with it. Not very much inductance, although it is there, but it's not worth really bookkeeping. It's got a parallel resistance. It's got a series resistance, which could be here or here, depending on how you want to put it. And then it's actually got the battery aspect of it, which is the perfect system that I just described here. Okay. So the question that we have is, what defines this RS and this capacitance and this? And I just talked about what defines this. This is defined by this. So, and of most importance, I think, is this and this. And what is a Warburg thing? So I'll cover that in 1 second. So now what I'm going to draw is a cross section of a real battery, of a real set of electrodes. Okay. So I have aluminum foil, okay? And then I have a thick electrode. In this case, it's going to be, actually, I'm going to be more honest about this. I've got lithium iron phosphate on both sides, all right? I want to maximize the use of my materials, my lithium ion battery, so for any given bit of aluminum foil that I have, I coat both sides of it with lithium iron phosphate, okay? And this is lithium iron phosphate plus a binder plus a conductive additive. Right, and it's made typically by either a spray coating or a slurry casting. You mix these nanoparticulate powders, lithium iron phosphate, with like some carbon black to help get good electronic conductivity, and a small amount of a binder, which is usually PVDF, polyvinyl difluoride, and it's sort of a slurry, and you can spray it and dry it, or you can blade cast it and dry it. And it's a roll-to-roll process that's done in bulk in battery factories. Okay, and then I have my separator. Okay, separator, which is a polyolefin or a polyethylene or polypropylene based porous film. Separators now for car applications specifically are starting to be smart, where if they get too hot, all the pores will melt together. It's called a breakdown separator, and it will disallow any lithium motion between the electrodes, and will then hopefully mitigate any serious overheating or shorting issues that might occur. And then I've got my anode is here. And this is, again, little chunks of powder that have the same kind of mix of stuff. And this is my copper foil. So if you take a lithium-ion battery apart, if it's wound or if it's prismatic, you're going to have, and then I've got another separator here, and it's ... okay? And I've got another separator here, ... So, and this is rolled up, or it is in stacks in a prismatic system, a true prismatic system, or there's a sort of a rectangular package that is actually a wound one of these that is sort of flattened, and that's kind of a common way of doing it too. There's many ways of putting these together, but this is the bottom line, okay? And these thicknesses now, depending, this is, I would say, 30 to 100 microns on one side, and this is going to be probably 20 to 80 microns. The specific capacity of turns out that graphite can hold more lithium per unit mass than most cathodes, so you actually need a little bit less. So if I have a 30 or a 40 or a 50 micron thick lithium iron phosphate, I probably need something that's a little bit less thick for my cathode, and density plays into that too, and there's some trade-offs, but in general it's a bit thinner. Okay, so now I'm going to erase this now, and now I'm going to talk about a real live cell. Okay, and this is where things are going to become more interesting.
What's the rough separation between the two?
Oh, they are at intimate contact. Okay, so the thickness of the separator is about 25, about 25 microns. And there is no open space. This is backfilled. So we wind these up relatively dry, and then we vacuum backfill it with our electrolyte. Okay. And the electrolyte infiltrates all the pore structure in both the separator and in the electrodes, but there's no wiggle room in here. These things are unlike a lead acid battery, which is like kind of sloppy inside, or you can shake it. These are what we call starved systems, where there's no free liquid inside of them. If you cut up a lithium-ion battery, you can't squeeze out electrolyte. It is fully infiltrated and absorbed into either the separator or the electrodes. Okay. And you don't want to put too much in because it's expensive stuff, so you want to have just enough. Okay, so now we can talk about some things that are probably more interesting to you. Now, I'm going to draw let's assume we have a regular, pretty benevolent or benign charge condition. We do a C over 5 or a C over 10. You guys are familiar with C rates? It takes C over 5 charge rate is a 5-hour charge. So let's do a C over 5 charge, pretty slow, and again, nice charge battery, okay? And then I'm going to do for any given battery, now I'm going to do some characterizing, okay? So I'm going to do some different discharges, okay? And okay, this is a discharge, and this is going to be in the x-axis is capacity in amp hours, and my y-axis is potential. Okay. Now, I've taken this cell, an arbitrary cell of arbitrary thickness, and I have discharged it under 4 different current conditions. Right, it's constant current discharge. Okay, and I'm going to say that this was C over 5. This was like I don't know, 2C. This is 5C, and this is going to be 20C. Okay, so it took me 5 hours to get this data, and I did the same thing at 2C, so half hour, shorter and very short. Right now, and so you can see I get much less energy out when I do the super fast current, the high current, as opposed to this very low current. Right, and concurrently, you are dropping whatever it is that whatever capacity you get out, you drop this much energy as heat. Okay, so this is like my equilibrium curve. Anything above it that you're not realizing in the amount of time through which you are discharging goes away as heat. Okay, and heat is bad, and I'll tell you why in a minute. But furthermore, there's a couple different things that are happening. If I had just a series resistance, all of my curves, so I'm going to draw an example down here. If the only problem with these batteries was that they had a series resistance in them, my curves would actually look like this, right? I would have my equilibrium curve like this, and then I would have my higher current. They would all just go over to here, okay? And then I would have my super high current. Right? All I would have would be this drop, and the difference between this voltage and this voltage would all just be scaled to the ohmic value of this resistor, right? But that's not what I see. In fact, I see a huge loss in overall capacity as well as a significant voltage drop, right? This significant voltage drop and this significant change in the profile of the curve is what we call concentration polarization, okay? And it has to do with, and this is really a key part of what it is that we need to figure out and understand about these batteries. And I would say the majority of the loss, so most loss of capacity at high rates equals concentration polarization. All right, what is concentration polarization? Imagine now, really slowly, I allow my, I'll stand so you can see it. Imagine now I've fully got a charged battery, all my lithium is in my anode, and I'm just going to concentrate on this unit cell right here. All my lithium is here, and I got a really slow discharge, and I let my lithiums easily diffuse through here, right? And they go through no problem, okay? Now, imagine instead, I almost short the cell, and I demand a huge amount of current. I allow, a 20C rate through here. What happens is that we essentially overstuff locally lithium. It builds up so fast. We locally extract all lithium that we can from the pore-filled electrolyte regions here, and concurrently, we cannot extract lithium fast enough from inside this structure. We become what's called locally starved of functional ions, okay? And this happens more rapidly the faster we ask the current to come. And the point at which we lose capacity or lose functionality entirely is the point where we have a region somewhere within our battery where we're out of lithium ions. There's no longer lithium ions at some point in this cross-section of this single cell where we just can't, there's no lithium left and the function stops. There's no more capacity, okay? The more current we do, the faster this occurs, okay? And that is captured in the equivalent circuit model by this Warburg coefficient, which is a diffusion-based, and there's probably multiple ones. There's one for the anode, one for the cathode, one for the separator, but we can just kind of lump it into one. The key with the Warburg is that it captures the ability of the lithium ions to actually navigate through my electrode structure and indeed navigate through the inside of my crystal materials as well. And it's a combination of all these different things. There is one weakest link, and it doesn't really matter what it is, but because we are actually moving these physical ions through the structure, they are rate limited much more so than electrons, which can flow very freely through all my metal stuff and indeed through all of the conductive additive that we have in our electrodes as well. And so we have the situation where when we ask a lot, and and this is where we have something very interesting. So let's say this is for a thick electrode, or this is for I'm going to say the red one is going to be my cathode is 35. No, sorry, my cathode is 100 microns thick. My actual composite cathode is right here, 100 microns. Okay, that's this curve. Now, let's say I instead do cathode equals 10 microns thick. All right, I've got a much thinner cathode, a much thinner structure, right? Well, if you think about that, that means that my lithium ions have a much shorter distance to diffuse as they travel between my electrodes, and that shorter distance is going to manifest itself in a lower limitation from a diffusion standpoint. So if I do the same thing, the same curves with a 10 micron thick cathode, I see the same thing for a C/5 rate, but then I see increased performance, right? So now the same curves for a 100 micron thick cathode gives me this capacity, but for a 10 micron thick cathode, I'm way up here, right? And the limit proof is that an infinitely thin cathode will perform fine irrespective of what current you ask of it, right? And that becomes a capacitor, right? And in fact, the intercalation electrode mechanism is very similar to capacitive interaction with respect to the way we talk about electrolytic double layer capacitors in this material system. But the point is that the thinner you go, the better off you are from this standpoint, right? But here's the catch. Why don't we just make really thin electrodes? It's because it costs a fortune, right? When you talk about putting 10 or 15 or 20 micron thick cathode layers on these foils and then rolling them up and then putting them in the cans and backfilling with electrolyte, you end up with a battery that becomes almost entirely foil, separator, and can. There's almost no active material. So there's this huge trade-off where we want to have the most cost-effective, cost-efficient batteries that can withstand a reasonable rate, but we don't want to make the electrode so thin that it's prohibitively expensive. And you know, the 10 micron thick batteries, they don't even make them, but if they did, they would be thousands of dollars a kilowatt hour, right? If you make 200 micron, 300 micron thick electrodes instead, you can get down into the $100 to $150 per kilowatt hour cost point, but you can't discharge it anything faster than a 5 or 6 hour rate. And if you do, you end up heating things up. So this gets me to the last point, and that is, why is heat bad? Heat is bad because of the electrolyte, right? Heat breaks down electrolyte. Okay? What that means, when I say breakdown, what happens? Well, it breaks down, and that wouldn't be bad in principle if nothing else happened, if it just decomposed and we were able to release the gases and it was all good. But it then coats the electrodes. So at 50 or 60 degrees Celsius locally, we basically end up coating our anode with lithium and fluorine and carbon-based stuff. So it's like lithium carbonate, lithium LiCFX, different. There's a variety of different things that end up precipitating out. But it's an insulating barrier that prohibits motion of lithium in and out of the system, and it limits electronic conductivity. And it also occupies lithium that we were counting on using for charge storage, and now occupies it in this inert thickness, this inert layer, and that's our capacity loss too, right? So as we cycle these batteries, this degradation is happening all the time, but it's very, very slow for low temperature, low rate systems. As we go at higher temperatures, higher rates, this degradation happens faster, and we will commonly see a more rapid loss of functional lithium, loss in capacity, as well as a faster buildup of lithium containing inert layers on the anode in particular, and that corresponds with higher resistivity and even more of this problem, of this diffusion limited problem, because now we have to force our lithium through this layer that's coating the electrode materials as well. Okay, so that's the enemy. And good, I'm doing pretty good. Right, so and what we then have now is in your system, for any given battery, for any given battery pack or any given cell, you really needed this kind of characterization, right? And the figure of merit is called the Ragone plot. Right, and it's, you're probably all familiar with this, but it's basically, watt hours versus watts at, so as it depends. Sometimes they flip it. Sometimes they put, I'll do it this way for now. Sometimes the discharge, because I believe that the independent variable is the watts that you use to discharge the battery and then how many watt hours you get out of it. Basically, batteries do this, something like this. So this is discharge power. And this is energy available. And indeed, for a perfect, and this is just what I described here, right? As I extract more, as I go to higher power, a higher current discharge, I have less and less energy delivered by the battery, okay? Supercapacitors typically look like this, right? And batteries typically look like this, okay? Supercapacitors cost a lot more, but they can function up here. At this high power, they give about the same energy that they give at a low power, right? Batteries, at a very low power, give their optimal energy. As you increase the power that you're pulling out of that battery, it gives less and less and less. This is due in part to this series resistance, but more profoundly, as you have a thicker electrode battery, more profoundly due to this diffusion limitation that I'm talking about, okay? So the key thing that you need to do, and for any given point, for cycling a battery anywhere on this Ragone curve, right, there's a certain number of cycles you can expect. You can expect, for good lithium iron phosphate batteries, if you live up in this region, you can expect, thousands of cycles, right? If you are way down here, really high power, because you're heating the cell up more, you're going to get less, right? It's going to be hundreds of cycles. Well, and maybe this is 10,000s of cycles, and this is thousands. It depends on what manufacturer you have. A123 Systems batteries, if you're way up here and you're doing really controlled charging, discharging, you can get to 10,000 cycles. And you can get thousands of cycles even in really bad conditions. But maybe the Thunder Sky ones are more like an order of magnitude worse. It depends. It depends greatly on how thick the electrodes are and all this. And these numbers indeed depend on electrode thickness as well. So as you look to characterize and understand what's important, you have to figure how thick are my electrodes, what's the overall energy density of the battery, and where am I living on this Ragone plot? How much power am I pulling? And how much energy am I getting out with respect to what I would get if I was at my very lowest power drop. So I'm going to stop right here and start and give you, let's ask some questions and have some discourse. So this is sort of like a really quick overview of the basic chemistry, what it looks like in an actual battery, and how I sort of think about the key performance parameters with respect to sort of, where these things should live and where you might. And one last thing, and this is why supercapacitors are so interesting, is that we really want to operate our batteries up here at low power, and in fact, the supercapacitor is essentially agnostic. So why not have a hybrid system that lives up here for the high power spikes, and we have very low rate charge discharge. Notionally, that's the best solution. Economically, it's very, very expensive to have these two different systems put together, and supercaps in general cost a lot of money. And I can probably come back. I don't have time today to talk about those, but I can tell you why at some later point. So that makes sense. I'm going to label this supercap. Okay, that's this curve right here. And this is battery. And so you could see why we would want to do a hybrid system, and all batteries are going to be more like this, and all supercaps are going to be like this. So anyway, that's enough. Questions, comments? How does this figure into what you guys are doing, and is this helpful or not?
Very helpful, I think.
Okay.
I have a
Question, is the capacity of the battery basically a function of the total volume of electrode and material? Is that the right way to think about it?
Yeah, more or less. I mean, it's a function of two things. One is this is the absolute materials function, right? Which is 140 milliamp hours per gram of this. So if I have something that's much higher here and I put it in the same structure, obviously it will increase. But for any given set of materials, it's the density and the thickness of this, right, and the overall size, right, of the battery. Yeah.
Can you talk a little bit about pulse versus constant charge and discharge?
Exactly. So thank you. That's where I was going to go with this. Okay. So given what I've just told you, that under really high currents, we sort of locally starve things out and we lose function. It turns out that folks have found in the past, there's a number of interesting papers, that you can hit one of these batteries hard with current and you do a couple of things. You locally heat it up a little bit if you have a short pulse, and that actually increases the diffusion kinetics a little bit, because as you warm it up, although long-term heat exposure is bad because of this degradation, short-term local heating is good because it greatly enhances the kinetic limitations that are associated with any chemical system, right? So you locally heat it up a little bit, you enhance local diffusion, but then you either let it sit for a couple seconds or you even do a little bit of a discharge whack as well, just to sort of equilibrate things and shake it around. And it turns out that by doing that, and there are, like I say, it's very specific to every individual cell thickness, cell geometry, thermal management approach, all that. You have to figure out what it is for individual cells. But there are pulse regimens for both charging and discharging that allow for, on average, a more efficient use of the materials than if you were doing a constant current, okay? And it has to do with the fact, basically, that the pulse allows you to increase the local heat a little bit to enhance the diffusivity without really impacting the long-term heat exposure, if that makes any sense at all.
How much more efficient?
It depends. It's a great question. I would say
20%?
no.
50%?
It's in like the
5%?
10% or less. It's not. I mean, you're not going to dramatically increase it. But if charge time, for example, is really important to you, you can charge using properly engineered cells. You could charge significantly faster by a pulse technique versus a constant current technique. How much faster? 40 or 50% faster.
I'm also thinking in the context of regenerative braking. If you're
Agreed.
braking faster than you then you can charge safely, and if you filled your super cap.
That's right. So, and here's what you would do. You would have some algorithm that would monitor, what's happening between these two. And maybe you've used the super cap along with some control electronics to always do the same optimal charge algorithm into the battery while having the super cap as a buffer, for example, right? There's like some optimal, there are certainly some really interesting fast charge techniques. I sent a paper around, I don't know if all you guys got it or not, but there's a handful of other ones. So I sent it to Illa and Greg and some other folks. So I'm happy to send it around to the rest of you too, or you can ask them. But it's documented and it's real for sure, and specific to that the regenerative braking pulses. It's actually really interesting, I think.
Is there a pull story for lead acid?
There surely is, and in fact, lead acid has. There's a couple of really interesting proprietary and/or patented charging techniques. Lead acid as a whole is so different. It's not even the same.
Yeah.
All the chemistry is different. All the problems are different. But that being said, lead acid builds up these sulfate layers on the electrodes, and it turns out that when you do it's actually much higher frequency charging. It's almost AC charging. You end up cleaning and stripping that sulfate layer more efficiently than if you just have a constant current charge. And you can do much better. I mean, if you have the right charging and discharging regimen for lead acid, you can do really, really well. And it's amazing how much better a good lead acid battery will do with the proper charging and discharging and associated care. And that's something interesting too to consider, is hybridizing lead acid with a supercap. And there's another class of batteries that are sort of right in the middle of supercapacitors and batteries, and like Altair Nano and now Toshiba, Panasonic is going to start making them too. And they basically have super high rate, very thin intercalation electrodes that have really almost no capacity fade. And their Ragone plot is somewhere in the middle, like this. And they're also really expensive though too, but you might end up using those instead of a supercap, you get more energy, at these higher rates, and you could still, maximize the efficiency of your system without having too much degradation according to the heating and all this that's happening. So that's another interesting. I hope to get some samples at some point, and it'd be really fun to play with those too, especially since you guys are starting to tool up and have like some legitimate stuff, which is cool. Yeah.
When you're talking about pulsing, charging, or pulsing, discharging to increase efficiency, can you get, and I know it's different for different cells, but can you give us like just even a rough sense of, are we talking hertz, kilohertz? What?
Oh, for these batteries, it's hertz or even slower, millihertz. Hundreds of hertz. And again, it's greatly dependent on the so there's a time constant associated. There's a diffusion time constant associated with the lithium moving through these electrodes, and that time constant depends on the thickness, depends on the porosity, depends on what we call the tortuosity. There's another factor called the rugosity. These are all materials properties. Tortuosity, rugosity, porosity, surface area, thickness. There's a lot going on in here that determine that constant, that diffusion constant. And of course it's an additive sum. But you end up with some value through which the duration of your pulses is going to be sort of aimed at that diffusion constant, time constant value. Does that make sense? I mean, the thing I don't have is, what you have to do is go through for your cells or your batteries or your pack and see what you think is happening. And you can pretty easily test it using, you can imagine setting up 4 or 5 different tests of different pulse duration and intensities and pretty fast rule something better or worse. But the effect should be there. You should see it, and you should quantify it, and then you can then map that up to what you want to do in a vehicle.
Another question I have about pulsing is through the natural PWMing of the inductors and the motors, which are happening kind of at the kilohertz level. Right.
Understood.
Are we then kind of, you drew this capacitor down at the bottom?
Sure.
Are we avoiding heating the battery because that capacitor is there?
Yes, at those frequencies, absolutely. I mean, you're almost looking at a high-pass, low-pass filter kind of thing at this point, right? I mean, this is going to be a low-pass filter at some point, right? This capacitance is a true electrolytic capacitance. It's not a electrochemical double layer capacitance. And this capacitance is simply, you've got foil, separator, right? And there's a dielectric constant associated with everything that's in between those foils. And it's a capacitor, right? It's going to be in the microfarads or something like that, or millifarads, depending on how big your pack is. A big pack is going to have multiple millifarads of electrolytic capacitance, right? But that's going to be important for some of these high-frequency things you're talking about. And I'm not sure, but I'm sure others have thought about it, but you might be able to use it. It might be interesting. It's compelling.
What's the degradation mechanism
of the batteries?
Why does my battery lose
its loss of lithium from the electrolyte leaves the electrolyte and forms a coating on my anode. And the coating is a placeholder is lithium carbonate.
So it's not intercalating anymore.
It's no longer intercalating. It's out of play, right? It's this relatively resistive. It's a benign coating, but it's resistive, and then it resists lithium transfer. But most importantly, it ties up this lithium, and that lithium's out of play, right? And you can't get it back out, right? And this decomposition happens more rapidly if you expose your batteries to high temperature conditions, because it's a thermally motivated kinetic decomposition, right? And so what you want is, and now there's so much proprietary activity these days in the battery world, but there are additives to put in your electrolyte to make it better. There are special coatings. One of the most interesting things is that how fast this decomposition happens in part depends on what the decomposition surface looks like to start with. And when I was at JPL, we were working with A123 Systems right after they got founded. We were working with them in like 2004, 2005, 2003 even, I'm not sure. But we were giving them some of our low temperature electrolytes that we were putting on the Mars rovers and so forth. And we wanted to send the cells back raw right after they made them, and they wouldn't do it. They had to take it through the formation cycling first, right? And the formation cycling, and my guess is they had some interesting pulse or some interesting different time temperature soak formation cycling that very uniformly and thinly coats the anode with a very thin layer of this stuff. You actually engineer this layer such that it's more difficult for subsequent layers to deposit onto it, right? So part of this whole why are some batteries good and so why are some batteries bad isn't even the chemistry. It's how you condition the battery after it's been made. And you can actually do a lot by doing a really good formation cycle and understanding how to optimize this coating. You take advantage of the natural fact that this stuff decomposes. You actually make a much more dense and robust layer that really is going to fight subsequent degradation.
What happens when we overcharge the batteries?
Oh, good question. So the good news is that lithium iron phosphate cathode material can handle overcharge all day long. Much unlike, so lithium cobalt oxide, you can't take all lithium out of lithium cobalt oxide. That's what's in your cell phone battery. And if you take more than half the lithium that's resident out of it, the crystal structure is not as stable and it won't last that many cycles. Okay, so the cathode in this case is totally stable. So the only enemy for this particular chemistry is the breakdown potential of the electrolyte itself. That's about 4.3 volts, right, or so over long term. You can go higher, but above 4.3.4.4 volts, you start to see electrolyte solvent, I should specify, breakdown. So this is equivalent to water electrolysis at 1.3 volts, right? You just do this, whatever this solvent is, it starts to split somewhere between 4.3 and 4.5 volts. It will just start to evolve into gas, right? When it evolves into gas, it pressurizes the cell, and if you do it too rapidly, there are vents built into all these batteries, right? All these individual cells. And if it happens slowly, it will vent. It will be a benign loss of function. The electrolyte will dry out. If you do it too rapidly, you can cause what we call a rapid venting event, which is an explosion. And when that happens, you obviously could cause the chance of a spark and subsequent ignition is much higher. And indeed, these are all organic, so they're full of oxygen and other sort of flammable components. So when there's one spark, and this is the famous the laptops that just blow up, right? You see, and if you look at one of those cells, it's usually a hole in the side where a seam in the cell broke before the vent did because there was such rapid pressurization because of a very internal short typically. And basically looks like a blowtorch coming out of it, right? And it's this organic solvent that's vaporizing and coming out and igniting and just spraying out, right? And it happens to all batteries that have this solvent. But because you are charging to a lower voltage, you have much more wiggle room before you get to this danger point. That's good. And indeed, this stuff will not, you split the oxygen because you're at this low voltage, you're going to be much less apt to be splitting the electrolyte at the cathode as well. So it's more safe. I would just standard 4 volts is what I would say, and you're going to be okay. Also, stay under 140 degrees C. Okay, that's kind of a magic number for this particular chemistry. If you dwell at high temperatures for a long time, eventually they will fail and they will blow up, maybe. It depends on who's making your cells and what the deal is. But if you want to have some fun, you might try that once just to see how it looks. It's exciting, especially if you expect it. It's just when it's not expected that you're in bigger trouble. But it's typically, if you're under 100 degrees C and you're under 4 volts, those are reasonable engineering parameters where you're going to be in a safe, comfortable place.
You said 50 to 60 C was bad for the electrolyte.
That's right. So I'm talking about safety now, not performance. Yeah, you want to stay under 60 C if you want to have long-term stability of your electrolyte. You want to stay under 100 C if you don't want to be blowing people's hands off. So, two very different points. Yeah.
What's a good way to measure temperature on one of these cells?
Good question. I mean, thermocouple is fine, or you could do. It depends on what you're. Basically, and I don't know what kind of cells you guys have, but what I would do. Do you guys have? Are you talking about the prismatic ones? They have a metal bar on the top, and then a plastic coating. Is that right? And you've got your 2 tabs here. You want to sync to something metal. All right. I would sync a small thermocouple to one of the leads out, because that lead goes down and is thermally sunk to the inside. Don't link onto your plastic outside. That's not going to help you very much. You really want to know what's going on inside. So, and you can get little tiny thermocouples and put them on.
Yeah.
don't use one of the battery packs I built had a active semiconductor temperature. It was a chip, and the chip was stuck onto the side of a metal can of the cell. And then we had a ground loop in the system, and it overheated the chip, and the chip boiled the battery. It's complete engineering irony, where the temperature sensor ended up blowing the batteries up. It was ridiculous. So yeah, I would avoid that kind of thing. And indeed, you want to be careful with syncing. If you do sync a thermocouple here, I'd make sure it's isolated, and you might even put like a milliamp fuse on it or something, just so you don't have any sort of current danger there. Because these things are pretty big and pretty scary if you're not careful. Sorry?
What's over discharge like?
All right, so over discharge, what happens at over discharge is that you actually end up so you take all the lithium out of the anode, right, and it all goes, this thing lives at the natural, when all the lithium is living in the cathode and there's no lithium at the anode, the natural open circuit voltage is about 1 to 2 volts, depends, and it's quite steep, so a very small amount of lithium change will take you up to 3.4 volts. So if you actually let it go below that, you could be plating lithium onto your cathode because you're driving more lithium over than it wants to be, or you could be causing some other decomposition or phase evolution on the cathode side. In my experience, lithium iron phosphate is relatively stable to over discharge. Now, if you go to a negative voltage, if you actually really over discharge it, all bets are off. I would avoid going below 0 volts. That's never good, because you are certainly going to be splitting your electrolyte in that case, right? The electrolyte's not stable below 0 volts. In fact, electrolyte is not stable below about 0.1 or 0.2 volts versus lithium, so you got to be pretty careful about going to negative potentials, because it's the same problem as going to over potentials. It's just like a water cell. If you go to minus 1.3 volts or plus 1.3 volts, you will evolve gas, right? So it's the same basic effects, but just on the other side. There's not... Yeah, and most people, you just don't want to go below a volt, I would say.
So why is it the cobalt cells kill themselves below a certain voltage?
Again, lithium cobalt oxide is a different bag. That material can accept more lithium, but it has a catastrophic phase transition, and it renders itself useless, right? Lithium cobalt oxide has a structure actually not too dissimilar from graphite. It's got these layers, and you can actually jam a lot of stuff in there, and it's not so good. And you will certainly if you allow it to go to 0 volts, it probably won't be good at all, period, after that. It's very unusual to be able to resurrect that. You'll screw up the crystal structure.
You're mentioning thermocouple connecting to kind of the metal parts of the battery.
Mm-hmm. Something metal, either the metal can on the outside or something, yeah.
Are there cases where it makes sense to heat sink the battery to something, and if so,
oh, sure.
attach the heat?
Yeah, and if you're heat sunk, and here's the question to you: there's cell level and pack level and module level thermal management and monitoring, right? And so it also depends on what your thermal management system is like. If it's air, you're not going to have a heat sink, right? If you're just blowing air through your pack, right? If you have, obviously, a thermal reservoir, I would do both. I would monitor the heat sink and whatever the reservoir is or whatever is flowing, and I would also monitor the actual tab out somewhere, or if you can contact a metal can somewhere. Just something that's thermally conductive, that's in contact with the electrolyte inside. What you want to get to is the temperature of the electrolyte. That's what matters, okay? And you also want to, and you can actually, that's actually an interesting thermal control question, is when my heat sink is this temperature, what temperature do I think my electrolyte inside the cell is, right? So you actually want to capture both. But once you do it for a handful of cells, then you can probably just monitor the heat sink and then have the data that shows what's probably happening in the cells. But indeed, if you, in particular, because you guys are looking at these different hybridization approaches, that's going to be something really interesting, is you're going to want to understand with and without supercap system, or with this algorithm or without this algorithm, what's my thermal environment like? And then there are a handful of reasonable models that directly map thermal environment to battery degradation, right? It's for a specific kind of cell and all these caveats, but you could actually start to make some specific techno-economic analysis points about, well, if I'm at this temperature, my battery's going to last this long. If I implement this algorithm, my temperature on average is this much cooler, therefore I should get this many more cycles out of it, and that's worth this many dollars, right? And that's kind of an interesting and compel. I always want to make, so I'm half-time EPP, so I always want to make a techno-economic case that's going to benefit society eventually, right? So that kind of data is very useful.
What about lower bounds on temperature?
Oh, so that depends also on this thing, on the solvent. Everything is dictated by this solvent. And as is, I would say you can probably go and expect reasonable. So here's the thing, too. There is cold crank, like when I first bias it, and then there is what happens after I run at a particular current for a couple minutes, because it self-heats, right? That's the good news about batteries, is that especially these batteries, they will actually self-heat. But with this off-the-shelf kind of stuff, you could probably go to minus 10, minus 20 C. I'd say minus 20 C is reasonable. And you're going to get some of this, right? Because again, at low temperatures, my diffusivity is going to be lower because it's a kinetically motivated process, and you're going to have more concentration polarization. You'll starve out a little bit earlier. But the good news is that you can actually, there's an argument for doing some pulsing at very low temperatures to heat up the inside of the battery. You're only going to heat it up a couple 10 degrees Celsius. You're still going to be well within your comfort zone because you're not going to be at 50 or 60 degrees C anytime soon. And in fact, you'll get better performance. And so there is, the question is, what is the, so at very low temperatures, what you really want to do is perform a current ramp, where you start with 0 amps and you ramp the current up at some rate to get heat it up, and let that happen for a couple minutes, and then you could start to actually use it more like you'd expect to be able to use it.
So if you go below like minus 20, are you damaging something? Or
no, you don't damage it. You can just freeze that. I mean, in fact, you could take these batteries, and in fact, we did this, or they did it under my suggestion for the Lunar X program. There's some undergrads working with Red, and they took some lithium iron phosphate batteries and they froze them in liquid night. The question was, under the 14-day lunar nighttime period, what happens to these batteries? Let's say we can have other things that can survive over this time without, any sort of isotope heating or anything. What happens? They froze them in liquid nitrogen, took them back out, thawed them out, ran fine, right? It's okay. You can freeze them, no big deal. And in fact, if you add the right stuff to your electrolyte, you can get batteries that work okay to like minus 50 C, minus 60 C. It's not unheard of, and and that's an interesting game to play. But typically, the lower temperature you go for performance and additives, by the curse of nature, you lose stability at higher temperatures because you end up putting all these extra additives in here that typically spawn a lower breakdown temperature. So there's like that game to play. Yeah.
Okay, we're now using these Thunder Sky 100 amp hour batteries. We're planning to probably run them up to continuous currents, maybe 200 amps. Is that crazy?
No, that's 2C, right?
2C.
Yeah, that's fine. I would monitor the temperature, right, and just make sure you don't go above 50 or 60 C. And when you do, I would back off. And I would, go through it and actually make a Ragone plot for one of those cells too. At this watt discharge, I get this many watt hours out before I get to 2 volts. At this many watts, I get this many watts. I mean, it's 10 different charge-discharge cycles. Always charge at the same low rate and then discharge at different higher, increasing rates. And then you'll get a sense of where, and the question is sometimes batteries have a very distinct knee too, right? Where you get nothing above a certain power. Obviously, if 200 amps is above that knee for your batteries, don't do it, right? You basically want to do a Ragone plot, and you want the highest current you want to use routinely is going to be somewhere above that knee, right? And so you want to sort of empirically determine for those cells what's going to make the most sense for you. But off the top of my head, I imagine that a 2C rate is totally going to be okay for these batteries.
Should we be thinking about other brands of batteries, or is that? I think you said Thunder Sky was good. I'm not sure why.
Yeah, well, they're less expensive, right? And they are. They're starting to make a fair number of these. I know the Robotics Institute folks, not Robotics Institute, the guys down in Lawrenceville used a pretty good sized pack of these on one of their hybrid vehicles, and they did okay. For example, it's mainly cost and availability. You can't. The best supplier of batteries in my mind of this chemistry is A123 Systems, but really all you get are the individual 2.3 amp hour cylindrical cells, and that's just a lot of issue. You want big cells. In Thunder Sky, you can get them right now, right? You can probably get some big ones from Valence as well. They're probably okay. There's many others that you can get, but they are pricey, really pricey. So this is
looking at high power. Do you know anything about them?
Yeah, they're fine. I mean, most of these. If a battery company is actually selling a device, unless they're Chinese and they're really undocumented, I mean, there's some you can buy LiFePO4 cells from unknown sources online right now. I wouldn't trust those at all. They could be really bad. They probably have a huge amount of variability. That's something else. As you start to put these things in a pack, be very careful that the strings are well matched. When I say and by saying that, I mean that you want to make sure that each cell in a string has the same capacity, right? Arguably, it should have. So here's an example. There was we were looking. This is again from my days at JPL. We were looking at lithium-ion battery packs for satellites, right? And there's two ways to do it. And you need to string up 10 or 15 or 20 cells in series to make a, whatever. Let's say we have 48 volt string, 48 volt bus. So we have 10 batteries in series, right? 10 cells in series, 10 4-point whatever volt cells in series. And if you wanted to guarantee lifetime, each one of those cells should be identical, right? So you either manufacture identical cells, which is very expensive, or there's a company in the UK called ABSL, and what they do is they buy 50,000 Sony computer batteries, and they test every single one of them completely, and they determine all these equivalent circuit units for every single cell, and then they use a matching algorithm to put 10 of them in sets in series together, and they put the most identically matched cells that statistically they can find. And what you end up with is a very nice battery pack that performs every bit as well for a much lower cost, because it's easier to buy 50,000 cells from Sony than it is to make 100 of your own that are perfectly the same, because of yield issues are killer. And when you string them up, you also, of course, want to take them to either, before you string them, you want to put them all in parallel and take them either to an extreme. You want to take them either extreme charge or extreme discharge. And this makes sure that they're all exactly the same state of charge. And you put them in parallel. Then you quickly switch them and put them in series, right? If you don't do that, you risk putting cells in series that are not well matched. They're not the same place in their charge cycle. And this is a real problem with lithium iron phosphate, because you have a very constant voltage curve, right? So one cell could be here and one cell could be here. If you put those things in series and try to cycle them, you're going to be extremely biasing one and the other as you charge and discharge. So you got to be careful with that as well.
Isn't the battery management system supposed to do that for you?
It depends. I would never suggest that a battery management system would be able to take individual cells offline. I think that's a waste of money. I think you have to do string level management. No one in the car pack business is doing cell level management. They're doing string level management. Yeah,
so we shouldn't be buying these little things that go on each cell.
Well, you can, but it's not cost effective. Again, this is the EPP guy talking. It doesn't happen in the business, right? In the business, they have well matched cells in series, and they monitor the voltages of the cells, but they are not able to take any individual cell offline to correct it. That's a very expensive proposition for a 30 or 40 kilowatt hour pack. It's crazy. And for example, the 5 kilowatt hour pack that I have on the CMU Prius, it has, I think, 5 or 6 modules of lithium iron phosphates. The modules are monitored and they have management going on, but each module contains tens of cells, each one of which is just dead in series, and there's no way to single out a single cell for maintenance.
They sell these battery management systems as a main computer or something, and
Sure.
then there's these things you stick on each
Oh no, yeah,
cell.
I'm quite familiar. Yeah, it's
But
just
you're saying
they don't do it. It's just not done. It's just too expensive. I mean, it's really
they're like 10% of the battery cost or something.
yeah, too expensive. It's just not done. They mean every dollar counts. I mean, even
Yeah.
at a cell level right now, we're at on a really good day. I mean, no one can do this. No consumer can do it, but at a really good day, like GM or Toyota can do $300 a kilowatt hour at a cell level, right? And when you throw in all the rest of the pack stuff, it's $500 or $600 a kilowatt hour easily. And we need to get down to $200 a kilowatt hour, right? So the design has to be, magnified simpler, right, in many ways. And part of that is you cannot tolerate that level of management. In fact, the level of management that we have now is probably too excessive for what's going to make sense on the long run. If you run the numbers and look at what the mass car market can bear and what people believe consumers are willing to tolerate from a battery cost standpoint, it's a huge disconnect. But the way to do it is to put on every single cell a management circuit. I totally agree. That's engineering-wise, that's the best solution. But mass production-wise, it's really expensive. So there's a difficult trade.
It's still not clear to me. You're saying we're not going to destroy our batteries if we don't have a battery management system.
No, as long as the strings are matched properly, you'll be fine, right?
We got to get them started off right.
You want to get them started off right. I mean, and you guys, I mean, for what you're doing, you probably should monitor each cell. I mean, that's another story, right? Depends on. That's different, right? But the Tesla Roadster has 7,650 cells in it. They do not have a battery management system on every single one of those cells, right? They just do not. They can't. In fact, they just put everything in a steel sarcophagus and assume it's going to blow up. And fair enough, If they lose a couple cells, they're like, that's okay. We'll just replace the whole thing. But that's a lot of love. It's a 53 kilowatt hour battery pack in a very small volume. Anything else? Was that helpful? Is there any other comments or points or?
Well, so in terms of cell matching, I'm just thinking about the model that we'll be purchasing.
Mm-hmm.
We're probably going to we might buy a couple more cells than we need.
Right.
We're not in a situation where we're going to buy 10x more or
Agreed.
10x more.
Agreed.
So you're recommending that we take the individual cells, try and make some estimate of R sub S and R sub P.
Yeah. Here's the minimum thing.
Just take the outliers out? Or?
Here's the minimum that I would do. Take each cell and determine the R sub S and the capacity of that cell. All right, and then plot on just a typical XY Cartesian plot where the cells live. Mm-hmm. Okay. And what you want to do is any given set of cells that you put together, you want to make sure they're neighbors on this plot. They want to have a similar series resistance and a similar capacity. Okay. You don't want to put this cell and this cell together. You want to put so basically you can actually look at it and you put your thumb up and you're going to have one that's out here and one that's down here, right? Yeah. Throw these out and then group them. And this is the pragmatic approach. It's not going to be perfect, but it's going to be a lot better. Then once you group them, then you put them in parallel, take them to an extreme state of charge, take them off of parallel, put them in series, and then monitor the voltage of each cell. But don't, and then that will allow you to tell what's going on with them anyway. But the side is that you guys, if you monitor the voltage of each cell, you'll at least be able to because hopefully the way you design it, you could always take out and swap a single cell out, or you can take a single cell if it's getting off of its charge cycle. You can just go in and do hand maintenance on that one and then be okay probably for a while longer. But and that's the thing too. You will find a really good battery cell manufacturer will just be like this. They'll all be the same, right? But Thunder Sky, I'm not so sure what Thunder Sky is like, but I have seen cells from other places that are just like this, And you try to put these things in a pack, you're screwed because you're totally, after a handful of cycles, they're all in different places and you don't know what to do. So I'll be curious to see. I've never seen this data for Thunder Sky.
How much variation should we expect?
Should you expect?
Yeah. So how much
variation? I would say, in a percentage standpoint, I would say this guy should be less than a couple of percent.
I won't know the difference between this manufacturer and this manufacturer.
Right.
If I only do this
Understood.
once.
So a bad manufacturer would be 5% or greater, right? A good manufacturer would be 1% or less.
Right.
Okay. In both directions.
Mm-hmm.
So when we equalize these, do we do it at full charge or full discharge?
Either way, you just don't want to do it right in the middle. It's going to be voltage determined, right? So if you go to 3.4 volts, they all could be anywhere, right? So I would go to either 3.6 volts or 2.9 volts.
Parallel them
and let them sit there for a while. Do a constant voltage current fade. Let your current go to nearly zero, and then take it off. And you know that each cell has been lined up with itself pretty well, and it is at roughly the same state of charge. And then you slap them in series, and you can start then doing your. I would recommend discharging because you don't want to play with fully charged batteries.
Yeah.
So, in general, that's the way to go. Whenever I hacksaw these things open, I discharge them first. It's certainly the right thing to do.
And you wouldn't expect any buildup of unevenness in charge in the individual cells over time?
No, if they're matched perfectly, especially if they're matched in capacity, you wouldn't expect much, right? You shouldn't. And indeed, but even a 1 or 2% mismatch initially magnifies over multiple cycles, right? So you want a pretty good. If you have to pick between this and this, you want to match to this first. Match to capacity first, series resistance second. But they're both important.
Okay.
I need to go too.
All right.
Thanks so much.
My pleasure. Was this reasonable? Was it addressing questions? Did it help? Good. That was my goal.
I'm sure we'll
today.
have more emails for you.
Right. Well, I could go back and give this same talk for supercaps too, and can tell you what's going on with those. There's similarities in some things, but a lot of differences too. So.